Hi everyone, I've got some more examples on the ideal gas chapter here. The first one is a guaranteed to be on the test kind of problem where we're asked to do a conversion. In fact, all of these are very similar to the kinds of problems that would be on the test, and there are some in the homework too, identical to this. So first one, a bicycle tire is inflated to 80 psi. Convert that to atmospheres. So it's just a conversion. And remember, we've got all these different pressure units, and so I'm giving you all the conversion factors on the front of the test, and we just have to be able to convert back and forth. And so what we find, if we look at those conversion factors, is that 1 atmosphere is equal to 14.7 pounds per square inch. That's our equality. That's our conversion factor. So when you do a conversion, you always start with what you're given. So we'll start with 80 pounds per square inch, and we want to convert to atmospheres. So that's going to go in the numerator. 1 atmosphere over 14.7 psi. So that is 1, right? This is equal to 1. We're just multiplying by 1. The psi cancels, and try that out on the calculator here. We've got 80 divided by 14.7, and I get 5.44. And that's all there is to it. So hopefully on the test, when I look at the exam statistics, we see 100% of students getting those conversions correct. That's my hope as your chemistry coach. All right, let's go on to the next one. Now make sure you do these before watching me do them. Excuse me. So a gas sample has a volume of 25 liters at 1 atmosphere. What volume will it occupy at 2 atmospheres? All right, so I don't know. I actually do know, and I'm guessing so do a lot of you, but let's look at it. PV equals nRT. So how are those related? Now, there's two ways to do this again, right? You can do it by writing PV equals nRT twice. Once, plug in 25 liters in 1 atmosphere, and then the second time, plug in, we don't know the liters, and we put 2 atmospheres, and then just divide the two equations, right? So you can do it that way. That will work with any problem at all. But you might also be able to look at this and see that if the number of, it's the same sample, number of moles doesn't change, gas constant doesn't change, and never will, and the temperature doesn't change. They don't say anything about the temperature changing, right? And so we know that PV is equal to a constant, so we can then go the pressure times the volume before we do this is equal to the pressure times the volume after we do it. And that, of course, is one of the gas laws, right? And so we don't have to memorize all the different gas laws. They're all built into the ideal gas law. All right, so let's plug it in and see what we get. So we get 1 atmosphere, the volume of 25 liters, and what volume will it occupy at 2 atmospheres? And volume 2 is what we're looking for. So when we solve this, we're just dividing through by 2 atmospheres, right? Get that to cancel. And so volume 2 is going to be half. I don't even need a calculator for that. 12.5 liters. So it's going to be half what it was. So these are inversely proportional, right? As one goes up, the other one goes down, and that's the way it should work. And think about that. We've doubled the pressure, and so it squeezes down, and the volume should be smaller. And you want to think about the concepts here while you do these so that you use that to check your answer, because it's easy enough to get things flipped around on a calculator or whatever. But then you can check and see, does that number make sense? I think it makes sense. All right. So hit pause, go on to the next one. Calculate the number of moles in 2.5 liters of an ideal gas at STP. So it's really important I ask you to memorize what STP is. And we could go through and plug in PV equals nRT for this, right? Because we know standard temperature and pressure. So we know the pressure, we know the temperature, and we're given the volume. So we could get the number of moles, right? We could do that. But we don't have to, because these STP problems are so common, and we use those a lot in stoichiometry problems too, that I asked you to memorize that there are 22.4 liters of an ideal gas in 1 mole at STP. And I really think that's important to have that number committed to memory, because it's a shortcut that really helps a little, right? And so when we set this up, we can actually just solve this as a ratio, or we can do a conversion factor with it. Either way, you know, whatever works and makes the most sense for you. You know, the conversion factor would be, let's do it as a conversion factor. I was going to do it as a ratio, but I just changed my mind. So the conversion factor way of doing it is you always start with what you're given. So I go 2.5 liters, and then I look at my conversion factor, and it's 22.4 liters per 1 mole. So that means I'm going to put moles in the numerator and the 22.4 liters in the denominator and solve that out, and that's going to work. All right, so 2.5 divided by 22.4. I get 0.1116 moles. All right, so hopefully that helps with some of the homework problems. Thanks, everyone.